Hello, welcome to Noise Control and Management. As you know, this is the 5th week of this course. Today is the 4th day of this particular week, and over this week we have covered two important things. One is how a Kunz tube works, and the second thing which we have discussed particularly in the last class was development of one dimensional wave equations if we are using radial coordinate spherical coordinate system. And for spherically symmetric propagating waves, we had shown that there is an equation for pressure, and the one dimensional pressure wave equation I will rewrite is 1 over r square del over del r square del p over del r equals 1 over c square del 2 p over del t square. So, this is the 1D equation, 1D wave equation for pressure in a spherical coordinate system. And likewise, we can also say that the equation for velocity is 1 over r square del over del r square del u over del r equals 1 over c square del 2 u over del t square. Okay. So, these are the two equations which we had described in the last class, and we had also developed an equation for the momentum equation for a spherical coordinate system. Now, what I plan to do is I will change the form of these equations so that they are relatively easy to solve. So, ultimately we want to solve these equations so that we understand how spherical waves propagate, and to do that we are going to do some mathematical manipulations so that it becomes or it comes into a format which is relatively easy to solve. So, we will start with the 1D pressure wave equation, and we will transform this equation into a relatively easy to solve format. So, first we will write the equation one more time. So, it is 1 over r square del over del r square del p over del r equals 1 over c square del 2 p over del t square. Okay. So, the first thing I do to this equation is I multiply both sides by r. So, if I am going to multiply both sides by r, this 2 goes away from here, and on the left side I have r in the numerator. Okay. So, that is one thing. Now, this is my right hand side and this is my left hand side. Okay. So, we will first work on the left hand side. So, LHS equals r over c square del 2 p over del t square. Now, we know, now let us consider a term. So, let us consider a term where such that it is, so let us consider this term. So, excuse me. So, consider this term, okay, which is second derivative of p times r with respect to t into 1 by c square. If I differentiate it in parts, what do I get? 1 over c square r times del 2 p over del t square plus p times second derivative of r with respect to time. Okay. Now, we know, so when we look at this, we know that r and t are mutually independent. Therefore, del 2 r over del t square is 0. Okay. So, if that is 0, then this term is 0. Thus, I can write this as, so I can write thus 1 over c square into second derivative of p times r over del t square is equal to 1 over c square r del 2 p over del t square. So, we compare this equation and the relation for LHS. So, I can go back and say that LHS of the wave equation is nothing but 1 over c square times second derivative of p times r divided by del t square. So, this is equation number, this is the first. Now, we will play with the right hand side of, I made a small mistake, this should have been called LHS and this is the right hand side. So, I will make these modifications. So, this is RHS. So, we have worked on the right hand side of the equation. Now, what we are going to do is we are going to manipulate the left side of the equation, which is 1 over r times del over del r into r square del p over del r. So, let us say how does it. So, the left hand side is 1 over r times r square del p over del r. The entire thing has to be differentiated with respect to r. So, if I do the differentiation, what do I get? 1 over r and then first I differentiate r square. So, I get 2 r del p over del r plus r square del 2 p over del r square. And this, if I take 1 over r inside the brackets, what I am left with is 2 times del p over del r plus r times del p over del r second derivative pressure with respect to r. So, this is LHS, this is my second equation. Now, we will modify this slightly more and then things will become all of a sudden simple. Now, we consider this term. So, we consider second derivative of p times r with respect to r and let us see what it means. So, if I am going to differentiate it, what does it mean? It is del over del r. I first differentiate it once and then I differentiate p with respect to r. So, I get p plus del p over del r times r. Okay. And now, I differentiate it one more time with respect to r. I differentiate it one more time. So, what do I get? It is del p over del r square, second derivative, this should be only the first derivative, it is del p over del r and then I differentiate the second term and that gives me 2 more terms. So, I get, if I work on r, then I get del p over del r plus r del 2 p over del r square. So, if I simplify this, I get 2 del p over del r plus r times del 2 p over del r square. So, this is equation 3. So, now if when we look at equation 2 and equation 3, we see that they are same, right, which means, so thus the left hand side of the equation I can also write it as, because it is mathematically same, it is equivalent. So, this is equal to del 2 p times r divided by del r square. This is equation 4. So, now I compare equations 1 and 3. So, RHS and LHS, they have to be the same. So, my modified wave equation is what? It is del 2 p r divided by del r square equals 1 over c square del 2 p r divided by del t square. So, this is another form of 1D wave equation for pressure in spherical coordinate system, or spherical coordinate system. Okay. Now, we look at this equation and compare it to the 1D wave equation for pressure in Cartesian frame of reference. So, what was that like? It was very similar. It was second derivative of p with respect to x is equal to 1 over c square del 2 p divided by del t 2. This was the 1D wave equation for p as a function of x and t in Cartesian frame of reference. Right. So, when you look at these two equations, they look structurally the same. The only difference is that in the Cartesian frame of reference, 1D wave equation has this, the operators, they work on p, while in spherical system they do not work on p, but they work on p times r. Okay. So, they work on p times r. So, the point is that we can use the solution of 1D wave equation and use that and get inspired by that solution to come up with a solution for 1D wave equation in a spherical coordinate system. Now, for this system, we had explained that the general solution was what? It was a function f1 into t minus x over c, right, plus f2 t plus x over c, and this we said is p of x t. And f1 represented in this one Cartesian frame a wave travelling forward, and f2 represents a wave which is moving in the negative x direction. That is what it meant, but this was in context of p x t. So, we can use similar approach and solve for and develop a solution for this equation. So, using analogy, we can say that the general solution but here the solution will not give us the value of p, rather it will give us p times r. So, p times r is equal to f1 t minus x over c plus f2 t plus x over c. So, this is the general solution. Or I can say that for one dimensional spherically symmetric wave, I can say that the pressure is what? It is f1 t minus x over c divided by r plus f2 t plus x over c divided by r. Okay. So, this is the general solution. Now, here f1 represents a wave which is travelling outward. So, you have a spherical wave which has a center, and f1 represents a wave. So, excuse me. So, here it should not be x minus c. So, I made a small mistake. Instead of x, I should have written r. So, it should be r over c and r over c here also. So, in this case, for a spherically symmetric wave, f1 is a function of t minus r over c, and it represents a wave which is travelling outwards. Okay. So, you have a center and the wave is propagating, the sound wave is moving away from the center and is going on in the outward direction. And f2 represents a wave which is coming towards the center, it is coming towards the center. Now, in this particular course, we will assume so what do we assume? We assume that there are no reflections. There are no reflections. So, suppose there is a point in air which is generating sound, sound spreads in all the directions, and the reflecting surfaces are either at an infinite distance away, or they are so far that by the time the wave reaches the reflecting surface, it is so weak that there is hardly any reflection. That is what it means. So, we assume that there are no reflections. So, in this case, then this term will go to 0, because f2 represents a reflected wave. So, in that case, P of RT equals f1, which is a function of t minus r over c divided by r. So, this is the general solution. Okay. So, I am going to rewrite. So, if there are no reflections, then P of RT equals f1 t minus r by c divided by r. Now, what does this mean? What this means is that any function which is of this form f1 t minus r by c will represent a pressure wave which is spherically symmetric. So, we will look at some examples. So, any function which represents this form will represent a spherically symmetric wave, and it will satisfy our one dimensional pressure wave equation. Okay. So, some possible examples of f1. So, one possible example could be P plus E j omega t minus r by c divided by r. This is one possible example. Here, wherever I am having t and r, they do not come by themselves, they come in combinations t minus r by c, right, and there is a 1 by r term because of this thing. Another possible Another possible mathematical function which will satisfy one dimensional wave equation would be p plus omega t minus r by c square. This is another possible function, and then of course I have to divide it by r. Another possible function could be a sin t minus r by c by r plus b cosine t minus r by c by r. This is another possible function. So, we can have infinite types of functions which will be valid solutions, possible solutions for the pressure wave equation, as long as t and r they come in groups, they come as a combo, that is t minus r c, they have to appear as that, and of course the entire function should be divided by r, because I have a r here in our general solution. Okay. So, in our course, in this course, we will assume that the function which we will work on will be of it will be a complex exponential function. So, in this course we will say that p of r t is equal to a complex number p plus divided by r e to the power of j omega t minus r by c, because of the fact that most of the real complicated pressure functions, time series functions, we can express them as sums of sines and cosines using the idea of Fourier series or Fourier transform, and because e to the power of j omega t minus r over c can be expressed as a cosine and a sine function. So, this kind of a function will help us understand very complex waves as well. Okay. So, in this course we will say that pressure, so in this case we will say, and because p plus is a complex number and so is exponent j omega t, if I am interested in the real pressure, then I just take the real portion of this. So, again this method of finding the solution is very similar to the method which we used in finding out the solutions for one dimensional wave equations as they are found in Cartesian reference frames. So, in this course we will say that p of r t is a real component of p plus over r e j omega t minus r over c, where p plus, what is it? It is the complex amplitude of wave, the complex amplitude of the wave. Okay. So, as we look at this solution, we make one important observation. So, this is an important observation. And the observation is that as r goes up, what does that mean? That as we are going away from the center, the amplitude of PRT decreases proportionally. Okay, it decreases proportionally. So, if I double the distance between the source and the microphone where I am measuring, then the pressure will go down by a factor of 2. So, this is a very important understanding, and just by understanding one dimensional spherical waves, you can now appreciate that suppose you have a machine which is making a lot of noise. Now, it is not necessarily a spherical source, but as you go far away from it, in general, especially for very lower frequencies, especially if there are no reflecting surfaces, as you go far away from it, if you double the distance, your sound pressure level or the noise which will be perceived by the microphone or the human ear, it will go down by a factor of 2. Okay. So, the SPL, the pressure will go down by a factor of 2. Once the pressure goes down by a factor of 2 in terms of decibels, this means that it is a reduction of 6 decibels. Okay. So, that is there. So, this is what I wanted to cover today. In the next class, what I plan to do is develop some sort of a similar solution for velocity, and then in context of 1D waves propagating with respect to a Cartesian frame of reference, we had developed an expression for Z, which is a specific acoustic impedance, and this impedance actually connects pressure and velocity. It connects pressure and velocity. So, we will develop similar expressions for spherical waves, and we will figure out what is the impedance for spherically propagating waves. So, with this I want to close our discussion for today, and I look forward to seeing you tomorrow. Thank you.